So today we are going to be starting with Cambridge IGCSE Chemistry Paper 6 Alternative to Practical May June 2025 Paper 62. So let's get started with this paper. The first question says, when heated, magnesium reacts with steam to make magnesium oxide and hydrogen gas. We know this reaction that a metal would react with steam to form oxide and hydrogen gas. Figure 1.1 shows the apparatus a teacher used to react clean magnesium ribbon with steam and collect the hydrogen gas produced. Okay, so basically over here in this gas range, we are collecting our hydrogen gas. This is our magnesium ribbon. This is our steam from where we are producing our steam, and over here we are collecting our hydrogen gas. Okay, so let's see what the question says. Name the item of apparatus labeled A. What is A? A is a gas that's visible in the diagram. That this one right here, this one is a gas range. The next part says, suggest how magnesium ribbon should be cleaned before use. Okay, you know that whenever you have a metal like this, or you have aluminum, magnesium, or anything, there's a problem with it, that it forms its oxide, and that oxide sticks to the metal. So you always, before using any metal, maybe it being magnesium or aluminum, you scrape it off so that the oxide gets off the metal, because this is your metal and it has an oxide layer on it like this, the green one layer. So what do? You take a scrape paper like this and scrape out the oxide so that the metal underneath is ready to react. Otherwise, what would happen? There would be a layer of metal oxide like the yellow layer, and the metal would not react. So what you're gonna do, you are gonna scrape off using a scrape paper. I don't know what you call it, but it might be a scrape paper. You're gonna scrape off using a scrape paper. State the purpose of mineral wool. The purpose of mineral wool is so that you could basically heat it from underneath like this, and water does not react with magnesium ribbon. What reacts with the magnesium ribbon is the steam. So the purpose is to hold back the water. Otherwise, the water would be just running in the tube, and that would create mess in the tube, which we don't want. So the purpose is to hold back the water in the tube. The next part states, draw two arrows on figure 1.1 to show two places where the apparatus should be heated. So now we are heating the apparatus, and I guess we should firstly heat over here the mineral wool so that we could create some steam, and the second place we should heat is the magnesium ribbon, because when heated, magnesium will react. So we have to heat the magnesium as well. During the reaction, a colorless liquid collects at point marked X. Suggest the identity of liquid X. Okay, over here some liquid is gonna accumulate, and we know the liquid is gonna be water. How? Because what's happening over here is that we have this certain kind of steam that's gonna evolve from here, and as the steams move through the tube, what's gonna happen when it's gonna reach this part, the steam is gonna what's going to happen to the steam? It's going to condense over here. So what's going to happen? Steam is going to condense, and it's going to form water droplets, which are going to accumulate here. So the answer to this one is going to be that it's going to be water. The gas collected in A is not pure hydrogen. Suggest why the gas collected is not pure. We know it's not going to be pure. Why? Because there is some air in the apparatus before we started. You should know that there is some air initially in this entire apparatus. There is some air. And what's going to happen is that when hydrogen is going to be, produced, this air is going to be first pushed forward. And firstly, in the gas range, air is going to collect, and then hydrogen is going to collect. So firstly, all the air that's in the apparatus is going to be pushed forward, and firstly, the first gas that's going to be collected is going to be air. That's why it's not going to be pure. Because we're gonna say that basically it's not pure because it has air in it. Let's move on to the next question, which says that a student investigates the temperature change when anhydrous lithium chloride. Okay, you have anhydrous lithium chloride dissolves in water. Okay, you're taking a salt, you're dissolving it in water, and you know some salts they give endothermic reactions and some exo. We're not concerned with it. We're just concerned with the experiment. We need to read it very carefully and we need to take our points. Use a 50 cm cube measuring cylinder to pour 40 cm cube of distilled water, okay, into a 100 cm cube beaker. Only the volume of water is 40 cm cube. Don't be confused by this 50 and this 100. It's just the volumes of the apparatus, not that of what we are using. Use a thermometer to measure the initial temperature. Okay, use a 2 gram sample of anhydrous lithium chloride and add it to water. Continually stir the mixture in the beaker using the thermometer. Measure the highest temperature reached by the mixture in the beaker. Empty the beaker, rinse the beaker with distilled water. Experiment 2 says repeat experiment 1 using a 30 cm cube of distilled water instead of 40. So what we are doing is that we are just decreasing the amount of water being used. You can see it in the next experiment as well. What we are doing is that we're decreasing the amount of water that we're using. Next says 25 cm cube of distilled water instead of 40. Next says that 20 cm of distilled water. The next part says that we're using now 15 cm cube of distilled water. So we're just decreasing the amount of our distilled water. And next is use the information in the description of the experiments and the thermometer diagram to complete the table. Okay, let's do it. Okay, we have mass of anhydrous lithium chloride, which is going to remain 2 grams for the entire experiment. So just write 2 grams. It's not being changed. 2 grams, and that's going to be 2.0. Don't forget the 0 because we have to write it in 2 significant figures. Next says the highest temperature, and we have to record it from the thermometer. So let's read it. That's 25, 26, 27. So that's 27.0. Because you know the temperatures are given till 3 significant figures, so we have to be careful. We have to write this 0.0, otherwise the marks are going to be deducted. 25, that's 29.0. That's 30.5. This one right here is 31, 32, 32.5. Then we have this is 34, 35, 35.5. And now we have to write the temperature change. How do we get the temperature change? This is the initial temperature. This is the highest temperature. We just have to subtract. So let's take out our calculators and calculate 22.5 minus 20. No, let's just take the final temperature first. 22.5, 27. It was 27. So it's going to be 27 minus 22.5. That gives 4.5. So there's going to be 4.5 here. And next is 29 minus 22.5. 29 minus 22.5. I always recommend using a calculator even if your math is good, because you know sometimes when you have the opportunity you just mess up things when you don't take advantage of the opportunities you're given. So always try to use it. 8. It's going to be 8.0. Then it's going to be 32.5 minus 22. And that gives me 32.5. 10.5. You know the temperature change is basically increasing. 5.5 minus 22, and that gives me 13.5. So I see that my temperature change is increasing, 13.5. It's continuously increasing from 4.5 to 13.5. Now I have to complete a suitable scale in the y-axis and plot results of my experiment from 1 to 5 on figure 2.1 and have to draw a line of best fit. So let's try our best to plot the best results we can. Firstly, let's select the temperature change scale. Over here, my smallest value is 4.5 and my highest value is basically 13.5. So I have to select a scale that fits these kind of values. So let me just guess how many blocks I have. I have 1, 2, 3, 4, 5, 6, 7 blocks. So I can make this like to go from 4.5 to 13.5. Okay, so 0, 1, that's 0. I have to start with 0. 5, 10, and this can be 15. So that's the best scale I could think of. Now let's draw. Volume of water. I should be sure that in the first I'm using 40 cm cube and the temperature range is 4.5. So for 40, it's gonna be 4.5. What's gonna be 4? Okay, now this one right here, this is 2.5, this is 7.5, and this is 12.5. And now I have to label 4.5. So I just thought of a new method, a new scale that could be even more effective. That what if I do something like this? I'm just trying scaling. Choosing a scale is a trial and error, I guess. 1, 2, 3, 4, 5. They tell they have different methods. I don't think if they work or not. Yeah, there's one method that works, but if O-level IGCSE scales, they aren't that tricky. So even if you just go by, you're gonna be good. 1, 2, 3, 4, 5. Here's 10. 1, 2, 3, 4. Let's see what comes here. So that's gonna be 1.0. That's 2.0. That's 3.0. Okay. That's 4.0. Then we have 6.0. That's 7.0. 8.0, 9.0, this is going to be 11.0, 12.0, 13.0, and we finally have 14.0. So now we're going to try to fill as many things as we can. On 40, we have 4.5. So on 40, we're going to have, this is 4, and exactly in between 4 and 5, that's going to be 4.5 right here. And now we're going to plot 6.5 on 30. On 30, it's going to be a solid 6, and then it's going to be a 0.5. On 25, it's going to be 8. On 25, it's going to be 8. And then on 20, it's going to be 10.5. 20, it's going to be 10.5. And then on 15, it's going to be 13.5. So 15 is going to be right here. And I have to draw a line of best fit. So I believe this one right here, the first one, is kind of anomalous because it does not fit my trend. I'm going to draw my line of best fit something like this. So something like this. Kind of seems correct, but I guess this one's gonna be my best fit line, and I have to extend it downwards. This one's not very pleasing, so let's just erase it and draw it again. I just recommend not erasing, first moving your hand over it smoothly. Okay, so this one kind of seems correct. Extrapolate the line on your graph in figure 2.1 to reduce the temperature change when experiment 1 is repeated with 45 cm cube of water instead of 40. So we have to extrapolate the line till 45. Let's try and do it. And the temperature change comes out to be this. Let's extend it and see what it is. That is 1.4. So it's going to be 1.4 degrees Celsius. Don't forget, there's a degree Celsius here. Next part says, The energy in joules given out when 2 gram of anhydrous lithium chloride dissolve is calculated using the energy equation. Energy given out equals to temperature change into 4.2 into the volume of water. Calculate the energy given out when 2 gram of anhydrous lithium chloride dissolves in experiment 5. Okay, so the energy given out is going to be equal to the temperature change times 4.2 times the volume of water. Volume of water is going to be, experiment 5, it is 15, and the temperature change is 13.5. It's going to be 13.5, and this is going to be 15. 13.5 times 15 times 4.1, I guess. It's 4.2. 850.5. So it's 850.5 joules. Estimate the temperature change when experiment 1 is repeated in using 4 grams. It's going to be double, obviously. Temperature change, it doubles. So it's going to be 850.5 times 2. That's 1701. 1701. Reason, because, double amount used and all that stuff you're going to write here. Explain why the results obtained would be more accurate if the beaker used in the experiment was replaced by a polystyrene cup. Because that's going to give you more insulation. And second thing is that's going to happen is your less heat loss. Hence more accurate results. So, explain why using a burette instead of measuring cylinder is an improvement. We know that burettes are more accurate and more precise. Accurate and precise. They have a smaller precision, so they can give more accurate values. Explain why standing in the beaker in the water bath is not improvement. Standing the beaker in water bath is not improvement because, that won't, that would basically increase your heat loss. You don't want heat to lose. That won't make your heat loss less. So basically, there's no use. That's not improvement because heat loss is not stopped. Heat loss will still continue to happen. Isn't stopped. You can say that heat loss isn't being stopped by this thing. We need to reduce the heat loss. Okay, a student tests 2 solid J and K. Solid J is iron 3 iodide. Student just dissolves J into water. Solution J is then divided into 4 portions. To the first portion of J, the student adds aqueous sodium hydroxide dropwise and in excess observations when added. What's going to happen is that since we have iron 2, so they're going to be green PPTs form and they're going to dissolve when you add in excess. Just take all these values from your table here. That when you have iron 2, what's going to happen? Green PPT, and they're going to be insoluble in excess. Oh, sorry. That was chromium that's going to dissolve. So, dissolve, indissolve. Not indissolve, that's going to be insoluble. You just don't have to worry for this, even if you make mistake, because you have an entire table. So, I never, thought of learning it. You could only learn it for paper 1 if you want, but not for this paper. Just don't even revise it. You have a table. To the second portion of J, student adds nitric acid followed by dropwise of barium nitrate. Okay, so what's going to happen? You're adding nitric acid followed by barium nitrate. This is going to be no change because you don't have a sulfur ion. Barium nitrate gives change with sulfur ions. Okay, to the third portion, the student adds silver nitrate. Okay, this is going to give you because you have iodide, it's going to give you a pale yellow PPT. To the fourth, the student adds 1 cm cube of chlorine. Okay, when you're going to add chlorine to your iron iodide, this is your iron 2 iodide, and you add chlorine to it, what's going to happen is your iron 2 chloride is going to form and your iodide is going to be displaced. So this is a brown solution. So what's going to happen is that when your brown solution is going to be formed because your chlorine is potentially displacing this iodine. So what's going to happen is that a brown iodine solution is going to be formed. So you're going to tell that your solution turns brown, or a brown solution is going to be formed. The next part says that tests on solid K are done. Table 3.1 shows the test, the student observations. You carried a flame test, you have a lilac flame color, that's going to be potassium ion. The remaining K is dissolved in water to form portion. Solution K is then divided into portion. To the first portion in a boiling tube, you add sodium hydroxide, warm red litmus paper at the boiling tube, damp red litmus paper remains red. This means that you don't have an ammonium ion. That was the test for an ammonium ion. To the second part of solution K, in a boiling tube, add about sodium hydroxide and a piece of aluminum foil. Warm the mixture. Effervescence, damp red litmus paper turns blue. That's going to be what kind of ion? That's going to be a nitrate ion. So this is present. It's potassium nitrate. State the conclusion about solid K that can be made from the observations in test 2. It does not contain ammonium ion. It doesn't contain ammonium ion. NH4 plus. Identify the gas given off. Obviously, that's going to be ammonia gas. When you test for nitrates, ammonia gas is given off. Identify, it's going to be potassium nitrate. You know it. That's going to be potassium nitrate. This part is easy peasy lemon squeezy. And now we come to our last part, which is going to be a kind of an experiment we have to design. Let's see what the examiner says. Magnesium sulfate is a salt, we know it. Magnesium sulfate is soluble in water. Okay, now he's telling us some details that we need to be carefully picking up. We need to highlight every detail he tells, so that when we're writing our the experiment, because all these lines we have to write the experiment, we at least know something that we can deduce from the top. The solubility of the salt is the mass of the salt in grams that dissolve in 100 cm cube of water at a specified temperature. Okay, now he tells that the mass of the salt that dissolves in 100 cm cube of water is the solubility. Plan an investigation to determine the solubility of magnesium sulfate in water at 50 degrees Celsius. Your plan must include how the solubility of magnesium sulfate in gram per 100 cm cube of water can be found. Obviously, you're going to calculate the mass because that's what they've told you. Okay, you're provided with solid magnesium sulfate, distilled water, and common laboratory apparatus. Okay, so let's start with our investigation. We have a blank paper here, so let's just annotate what we are gonna do. So we are gonna have some magnesium sulfate. This is MgSO4. And what are we gonna do? We have to basically test its solubility. So what we're gonna take is what do we have to find? We have to find the solubility at 50 degrees. So we're going to set our temperature, and we have to include how the solubility in gram per 100 cm cube can be found. So let's get started with the drawings. First, I'm going to just draw everything, show it to you, and then I'm going to tell you the steps. So now I've put all my imagination on a piece of paper, and according to me, what I would do if I was in the lab, first I would take the piece of magnesium sulfate over here, and then I would take my water. I would just heat it, and you guys are also going to do the same, because we have to check the solubility. We have to check it at 50 degrees Celsius. So we're going to heat it till 50, maintain the 50 degrees Celsius temperature. Then we are going to add some known mass of magnesium in portions slowly, and calculate the mass we are adding, so that we are sure about the kind of mass we are adding. And after we have added the magnesium sulfate, we're going to use a stirring rod to basically mix it so that it just gets dissolved, and we are going to find the maximum amount of mass that dissolves. Finally, when this undissolved mass appears, this is the undissolved mass. When it appears, we're going to know that finally now we have to stop dissolving more. And we can then, what do is that we can use a filter funnel lined with a filter paper like this. This is a filter funnel that is used, and we can place a beaker underneath it, and we can filter our solution. And on the filter funnel, what's going to happen is that our sulfate that does not dissolve here would basically be present here, and the remaining mixture can be filtered. And now we can calculate the solubility by knowing the mass of the magnesium sulfate that dissolved because we added a known mass and we were adding known masses. And the volume of water that we're going to take initially is 100 cm cube because that's what we are told. And now you just have to write all these 3-4 pictures in your words. And that's going to be simple and easy tasks. What we're going to do is that first we're going to heat water till 50 degrees Celsius. Try to maintain its temperature. Because we have to check at 50 degrees Celsius solubility. Maintain its temperature. Next, what we're going to do is we're going to make sure that we have 100 cm cube. Okay, we can do this first. That's why I left one line, because I know that you could obviously add later on. Take 100 cm cube of water. Okay, now what we can do, the third step can be add known masses of MgSO4 until no more dissolves. And then what we're gonna do is the next step is gonna be easy. It's gonna be filter out the first. If you guys have time, just draw the pictures, because when I drew this I exactly know what I have to write on this page. So it's gonna be easy for me. Filter out the excess MgSO4. The next step is gonna be to determine the mass of the solution now that's left. So now determine the mass of the MgSO4 that dissolved, and make sure that it is in grams, because we have to find in gram per 100 cm cube, and that's how we're going to find it. It's easy, it's very easy. So important thing that you should not mix, you should not miss is that you have to keep stirring the mixture. That's really important. So I'd write over here, keep these are important details at this step. So you have to keep stirring the mixture to make sure all the magnesium, to make sure maximum amount of MgSO4 dissolves. So you know the exact solubility. And that's how we're gonna go with this experiment. And finally, we're gonna figure out the solubility. We just have to then determine the mass of the thing that dissolves, because we already calculated. And with that we end today's paper. I hope you liked it. Do consider subscribing to the channel, and that's gonna mean a lot.